The goal of this video is to understand the behavior of frictional forces and to be able to apply them to objects that are either at rest or sliding along a surface. Here's a man pushing a large mass on a floor. A free body diagram of the block would look like this, which would indicate that the block should accelerate rightward. However, you should know from experience that if you lightly press on a heavy object on the floor, it will not tend to move. There must be another force at play that is in opposition to the motion of the object. We call this force friction. An important realization is that if you press a little lighter on the object, it doesn't start accelerating toward you. If you adjust the strength with which you push on the object, the force of static friction adjusts to match your push. If you barely press on the object, the frictional force will be rather small. Pressing a little harder, the frictional force increases. But eventually, you will overcome the force of friction and the box will begin to accelerate. While the box was sliding, a frictional force continued to act on the box to bring it to rest. And this frictional force must disappear entirely once the box stops moving. So we have two different types of friction: static friction and kinetic friction. Static friction is the friction that tends to keep resting objects at rest, whereas kinetic friction is the friction that brings sliding objects back to rest. Friction occurs between two objects that are sliding against each other, in this case the block and the floor. Accordingly, the frictional force is proportional to the forces acting on the objects due to each other. Acting on the block, this is the normal force, a relationship easily verified experimentally. The constant of proportionality is written as mu. Static friction is proportional to mu sub s, and kinetic friction is proportional to mu sub k. We call these the coefficients of friction. But as we saw, these forces behave differently from each other. Static friction can take on a range of different values up to some maximum, so we express the force of static friction as an inequality. The force of static friction is less than or equal to the coefficient of static friction times the normal force. Kinetic friction, on the other hand, remains roughly constant, so we express it as an equality. The force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. The coefficient of static friction is generally larger than the coefficient of kinetic friction. This means that as we press on the box, the force of static friction will continue to match the strength of our push up to some maximum value. But if we press too hard, the block will break loose and begin to slide. Kinetic friction takes over at a value smaller than where static friction left off. If we choose some values for the coefficients of friction and for the normal force, we can plot what the force of friction looks like as a function of how hard we push on the block. The force increases 1 to 1 with our push until we hit some maximum value, and then it drops to the value of kinetic friction. Kinetic friction will have some small variations, but is roughly constant at the value mu sub k times the normal force. This region of the plot then represents the range of static friction, and this region is where kinetic friction is at play. Notice the force of friction is proportional to the normal force, and not necessarily the weight of the object. If we place our block on an incline, then the normal force will not be the same as the weight of the object. Let's say our incline is at an angle theta to the horizontal. The normal force points perpendicularly out of the incline, canceling out the portion of the weight that is pressing the box into the incline. Part of the weight is also pointing along the incline, and this is what our frictional force will work to counteract. This triangle formed by our incline, the horizontal, and the vertical is a similar triangle to this one showing the components of the weight acting into and along the incline. This angle is the same as this one, theta. This means the cosine of theta will be equal to the magnitude of the normal force. So the normal force will be the weight of the object times the cosine of theta. Because the normal force decreases with the cosine of theta, so will the force of friction. Of course, if we know the box is at rest or simply not accelerating, then I can simply say that it is counteracting the portion of the weight pulling the box along the ramp, and could calculate it directly. But this only works if we know that the forces are balanced. Let's take an example. A penny spins on a record. How fast can the record spin while keeping the penny in place? Because the penny is traveling in a circle, there must be a centripetal force acting on the penny. This centripetal force is provided by the force of friction between the record and the penny. Because the penny is at rest relative to the record, we use static friction to solve this problem. If I'm looking for the biggest possible force of friction, I can turn the inequality into an equality. This maximum frictional force is acting as a centripetal force, and centripetal forces are equal to m times the centripetal acceleration, which is just omega squared times r, the radius the penny is spinning on. Equating these terms, I have on the left the maximum allowable force of friction, and on the right, the force necessary to maintain circular motion. This will return the maximum possible rotational speed of the record. Since the normal force is simply balancing the weight of the penny in this case, the m's will cancel out of both sides of the equation, leaving a simple expression for the maximum speed of rotation that allows the penny to remain at rest on the record. We know, or can easily measure, the size of the record. We can approximate the coefficient of static friction between the penny and the record is about 0.1. Plugging those numbers into our equation, we see that if we place the penny on the outside of the record, it will remain at rest up to about 46 RPM. If we move the penny toward the inside, we can get the record spinning as fast as 69 RPM before the penny starts to slide off. The fact that it's much easier to maintain circular motion on the inside of a rotating platform should agree with your experience if you've ever ridden a playground merry-go-round. And if you haven't, you are strongly encouraged to find one and verify this result for yourself.